Okay, so most of you were here last time, I assume. We went through the course rules and what to do this semester. Actually, some of the things we did here, but if you have any questions about generally about the course, you can come and ask me. And but most, I mean, pretty much everything I said last time is on stars. Okay, so everything I said last time is on stars. So if you have any questions about the course, come and ask me. I'm not going to repeat it today. Okay, so that's the thing. In terms of the course material, we just did some introduction about set theory, how to use the set notation. We did the sigma notation, so you didn't miss much either if you weren't here. Now, today's topic is mathematical induction. And I advertised this a little bit last time about how important it is. We'll be using this as a concept in many weeks in the semester later on. So the idea is you have some statement depending on integers, indexed by integers, and you want to verify that this statement is true for all positive integers. So some of the examples that we have, for example, we'll be looking at example, show that 2 to the n is bigger than n squared for all n bigger or equal to 5. Or example, show that, say, some of the numbers, say cubes of numbers, is like, okay. So the statements, equalities or inequalities, will depend on n, okay? So we'll have statements which depend on n. Sometimes it will be more subtle. There will be more complicated examples. So this is the statement of induction. Suppose that we have an infinite collection of statements S1, S2, S3, and so on. At the beginning, we will be starting with some S1, but later on, like in this case, it starts with 5, so we will allow the flexibility that it can start with 5. But at the beginning, we will be starting with 1. Okay? Collection of statements indexed by integers. So that means we'll use integers to index them. So each of these SIs are just statements. Okay? So, for example, in this case, say S5 will be this statement. Something like that. So it's just a statement, and most of them you will be able to check if they're correct at a given S. So like S5, you can check it by calculating all the cubes, summing them up, and checking if this is true. For example, we can do S3 actually. So this is 8, this is 27, this is 1, you get 36. And on the other side, it says it should be this. which is 6 squared. That's 36 too. So we can verify these statements by direct calculations. Potentially, they're easy to check. But we have infinite many of them. Okay? So this is the key thing. Each of the statements are easy to check, but we have infinite many of them. Okay? And we want to prove or verify that they're all true. So we not only want to show S3 is true, S4 or S5, up to S1 million, it's not enough for us. We want to make sure that all of them are true. Okay? So any number will not do it. We want to show all of them are true. So this is done by mathematical induction. All these statements will be true. So this is the statement. So I prove by mathematical induction. So this is the idea. Is obtained by proving two statements. So we want to show all of them is true, and we will have a way to do this. So we'll have to check two things. First, check or verify whatever the first one in the sequence is true. Okay? So prove that S1, in this case S1, verify that S1 is true. Okay? This is relatively easy thing to check. Most of the time they're just easy checks. And in this case S1 is just 1 equal to 1. Second, this is the thing. Show that for any n, if Sn is true, then Sn plus 1 is true. So this for any n means anything that bigger than 1. So for any n, you verify that anytime Sn is true, Sn plus 1 must be true. And you may say, okay, this is also infinite many things, but this is relatively easy in infinite many things most of the time. So we'll be able to show this very easily. But if these two is true, then Sn is true for all n. Okay, so what does this do for us? Let me show you one. The logic behind this is this. You have infinitely many blocks. Okay? This is your S1. This is your S2, and so on. Now, the first statement says S1 is falling, is tipped and falling down. So this is the fact you know. You know this fact that S1 is being tipped. The second fact we know is that these dominoes are placed in such a way that if one falls, the next one falls. Placed in such a way that if one falls, the next one also falls. So if you know these two things, can you say that for any integer n, any, this is the key thing, the nth one will fall eventually? You can say that, right? give me any n, 1 million. It may take a while, but it will fall. We know that by these two rules. If first one falling, and if we know that any time one falls, the next one will fall, we know that eventually it will come to this. For any n, it will fall. Right? That's the logic. So this is how it works. Anytime one falls, the next one falls. You have to show, you have to verify, and you have to verify first one is falling. Okay? And we're not saying infinitely. It is not an infinite statement. It's a statement about all n. Okay? So again, n is some finite number, but so we are not saying. I mean, it will take infinite amount of time, all of them falling. So we are not saying all falling. We are saying in the end will fall. Now that's logic. That's the statement. Now let's look at how you use it. Okay. So to use it, we'll use these two examples. I'll show you one by one. Let's start with the example 2. That's easier. So this is first example. This is second one. Let's start with 2. We'll use this idea, this method. Okay. So this is called the method of mathematical induction. So this is the method. You'll solve very complicated questions using this method, especially in graph theory. For example, we'll use this method. So just remember the method, and that's the question we'll be solving. Okay. So solution of example 2. Now we already identified that this statement Sn is the statement, is the equality. That this cubes of these numbers up to n is equal to n times n plus 1 over 2 squared. You can actually check a couple of values if you want to verify this. So Sn is this. So we want to show Sn is true for all n. And using mathematical induction. Okay? So all I have to do is check 1 and 2. That's what it says. Okay? We need to check 1 and 2. So one said S1 is true. The second statement said anytime Sn is true, Sn plus 1 is true. So what is 1? S1. Is S1 true? So one says 1 cube is equal to 1 times 1 plus 1 over 2 squared. This is exactly S1. Is that true? Is it true? Yeah. This is 2 cancels with this. 1 square is 1 cube, so it's true. Very easy to check. It's most of the time the first value to check will be very easy. For example, with 5, we'll be checking 2 to the 5 bigger than 5 squared. 32 bigger than 25. We say, okay, it's true. We'll move on. So the first statement is always checking the first thing here. And it will be always easy to check. The second one is harder. Okay? So we need to show, if we use the notation from the last time, we need to show that Sn implies Sn plus 1. So for all n, we need to show this. Okay. Anytime Sn true, we need to show Sn plus 1 is true. Now this will require some arithmetic. Most of the time you will have to do some computations. Okay? So we will consider this 1 cube, 2 cube, n cube, n cube. So I need to show with the n plus 1 means this needs to be shown to be equal to n plus 1, n plus 2 over 2 squared. Right? So we need to show that eventually we want to get to this thing. The between we will fill in, okay? But we will need to start with this sum and hopefully get to this sum. Okay? Any ideas how I can get to that sum? Huh? Yeah, we can use the fact that we know Sn is true. So Sn tells us that the sum of the first n cubes of the first n is already equal to this. We already know that because we already know Sn. Okay? So by Sn, we already know this is equal to n plus 1 over 2 squared. This is the key thing. In all the induction, you will have to use Sn.
Excuse me. I have a question, example 1. I think when n is bigger and equal to 5, it's not correct. Because when n is 5, the equation is not correct.
But 2 to the 5 squared. Square, yeah. So actually this question is stated as what is correct. So you could argue that it's not correct. But it will be true for after 5. And it is true definitely for 5 because this is 25, this is 32. Okay. I also will solve it after this one, okay? So we first do this and then we'll solve that one too. Okay, so putting Sn, I get this thing. Hopefully, it'll get us somewhere. Okay, so this is what I got so far. And I need to show it is equal to this. What will be the most reasonable arithmetic trick to do here? Should I take the squares and cubes, try to add them up? Division? Subtract? What? Okay, let's go from here to here without setting equalities. Let's try that way, okay? But the idea you have is correct, that I have to make it factors look similar. So there's a factor here, n plus 1, so I should use the fact that there's n plus 1 here. So what should I do? Huh? Take n plus 1 as a factor out. Okay? So what is left is n squared over 4 plus n plus 1. Is this equal to this? Yes or no? Okay, what is this equal to? Let's take 4 this side, and then it will become equal to this, right? So what is this equal to? This is equal to n squared plus 4n plus 4. What is that equal to? Yeah. So this is equal to n plus 2 squared. Because when you open the square, you get 4 and 4n. So this is equal now. No, we verified that. Okay. This is what you need to do. If you feel more comfortable by setting up equality and do cancellation, that's also possible. But make sure you don't make mistakes that way. Okay. This is more clear. You start with this, use Sn, you get the equality you wanted. Okay. So what we verified is that this is true. Okay. So Sn plus 1 is true. We verified the second statement, the one we wanted to verify. And then this by mathematical induction, we can conclude that Sn is true for all n. This is what it does for you. Okay? Let's do this one, and then I'll give you a difficult one. Okay, so example 1 solution. The difference, big difference, is that we said we have infinitely many statements starting with S1, and we need to check S1 and then verify it for all n. Now, when you start statements from 5, you can just say, modify this a little bit more. You can say, suppose I have statements like this. It really doesn't matter, right? It starts with k. Now, I want to prove it's true for all n bigger or equal to k. I want to only prove after k. And then I need to check first as k is true. And then I need to show n implies this bigger or equal to k. That's all you do. Everything else is same. This is a little bit modified. I call it modified. Then we'll do a generalized one as well. But this is modified. This is easy modification. All you need to think is that the first blick is sk. And k could be any number, like 5. It doesn't hurt us. Okay. Okay, so that means we will prove this using mathematical induction. Just to emphasize that we start with a modified one, starting from n equals 5. So normal induction usually starts with 1, okay? So this is a slightly modified version that it starts with 5. So we need to check, first we need to check S5. So S5, we already discussed this. It says this is 25, this is 32. It says 32 is strictly bigger than 25, which is true. Okay? So we don't need to do anything else. It's just the easiest statement. Okay? The second one, we need to show Sn implies Sn plus 1. So and we only need it for bigger than 5. This is the key. Actually, you will not be able to show, in this case, that Sn implies Sn plus 1 for, say, n equals 3. This won't be true. It will only be true under this assumption. So don't forget that assumption. You are above 5. Above 5 is the key to prove this. You cannot show this unless you're above 4, above 5. So let's do that and see how it works. So we need to start with, I just say consider, we need to start with 2n plus 1. Right? And then eventually get bigger than n plus 1 squared. I mean, eventually we want to get this somewhere. So it's 2 times 2 to the n. This is the hint. What should I do next?
It's bigger than n squared.
Use the fact that this thing is actually bigger than n squared. So use Sn, which says 2n bigger than n squared. This is the key thing. You have to switch some point somewhere between these 2 to the n's to n squared, something. Okay? So the question is 2n squared some way related to n plus 1 square? Is it bigger? This is what we need. So actually we need equality. This is our question. This is what we need. Okay? If this is true, then we're done. Okay? So let's focus on that question mark. Okay? So we have 2n square, question square. How can I verify this? Any ideas? Take the square root of 2 and n plus 1.
You can solve the equation inequality.
Huh?
You can solve the inequality
Directly.
by taking
Take the square. Is it what you... This is another idea. And what do you do?
n square.
Cancel the n square at 2.
Then we just solve the equation.
N square minus 2n minus 1. How do we know if n square minus 2n minus 1 is positive?
We
Or
can
not?
find the roots and keep the
Okay.
roots.
So what are the roots? Do you know the root formula? Minus b plus minus square root of b square minus 2a plus 2 divided by 2. So what are the roots? 2 plus minus, or yeah, 2 plus is
Yani içeride 4 yazmam gerekiyor mu? 4 arada.
4, 8, 2. So 1 plus minus square root of 2 is. So what does it tell me? This is a parabola going up, n square minus, these roots are these points, 1 plus square root of 2, 1 minus square root of 2. So there's. So when is it going to be positive? This parabola. When is it going to be positive? It'll be positive here, right? And also here. But we're only interested in positive end. So will be positive, will hold, if n is bigger, equal to 1 plus square root of 2. Okay? What is square root of 2 is about? 1.4. 1 plus 1.4, 2.4. So this is about 2.4. So if I'm bigger than 3, I'm okay. So I'm bigger than 5, I'm very okay. So we're good. We solved it. Right? So we verified this statement for n bigger than 5. Any questions? Some of you may say, okay, this parabola drawing is a little too complicated. You could also done this. Like when you get this like this, you could say this is n minus 1 square, right? You get n square minus 2n minus 2. And then you could say, okay, this is bigger than 2. So you could actually use some other arithmetic. Okay, this is possible. But this is a little bit more creative. Like you have to come up with how to complete a square and things like that. But if you can come up with this, you should always be able to solve it using calculus. Okay. Okay, this is. Now there is. Let's see how much time we have. There are more questions like this in the book. But I feel like there is one difficult question I read last night, and I feel like discussing that one. See how, if you also enjoy it. I mean, this is a little bit harder than a typical question that you may come across in this induction section. But I sort of like this. This is called Hardy's lemma. So it's and I found it in this book. So again, I repeat, this is a little bit harder than what you face. So we have two collection of numbers ordered like this. So n numbers like this, n numbers for b's. And suppose that we're supposed to pair them, okay? Suppose that we have to make n disjoint pairs from these collections. So you just pair A's and B's. There are n A's and n B's, so they can be paired one by one, right? Now, the sum of these pairs, the sum of the products of these pairs, is maximum when AI is paired with BI for all I. It says that the maximum possible sum you get out of these products of these pairs is when you pair A1 with B1, A2 with B2, and so on. And this is a fact, doesn't change what these n numbers are. For any given n numbers, anytime you want to pair them, the maximum number you get from these pairs summed up is the one that you do one by one, like things paired across. Let me give you an example, and then we discuss. So example is this. So you get 1, 3, 10, and then 2, 4, 7. Now you wanna, this is your A1, A2, B, A3. This is your B1, B2, B3. One possible pairing, you could do A1, B2, like you could do 1, 4, say 3, 7, 10, 2. These are all possible pairings. So you can pair this with this, with this, and this. Other possible pairing is we could pair 1 to 2, and 3 to 7, 10 to 4. And so this is say called regular pairing. Regular is that 1 pairs 2, 3, 10 pairs 7. In each of these pairing, calculate this number. 1 times 4, 3 times 7, 10 times 2, and add them up. Okay? We had 4, 21, 20, 40, 5. Right? 2, 12, 70. There's no competition, it's so big. 94. 2, 21, 40, 63. So you multiply the numbers, you sum them up. The statement says, whatever the pairs are, whatever the numbers are, this is always going to be the maximum. 84 mü? Yanlış hesapladım. Doğru. You can try all the pairings. You can sort of say, okay, 70 and 4, 6, 80. I guess you could get, I mean, if you pair this and you do this, you get 80. Still not 84. It's below 80. Always maximum is this one. And it doesn't matter what the numbers are. Some of them will be minuses. Some of them. As long as this order is the case, the maximum sum of the products is obtained by this way. This could come up in somewhere, right? You could be trying to find some maximization problem for a pairing. I don't know. And to know this fact is nice. It's a nice fact, right? You don't have to try all the possibilities. It tells you from beginning, this is the best way to do it. So let's see if we can prove this. We can verify this statement. So why should I try to prove this? Is there a, first of all, this is a statement about general n. So this statement here is for a general n. So this is your Sn. So we'll use induction. This is our Sn. So Sn says that anytime you have n many numbers, and if you're paired, this is the way to do it. Actually, and for one, the statement doesn't say anything, right? So we can say our claim is that Sn is true for n bigger or equal to 2. So we can assume that n is at least 2. We'll use this in the proof. Because if we don't know n is bigger than 2, we cannot separate out some pieces. So for 1, it doesn't say anything, right? So if there's one number here and one number here, there's only one way to pair them up. And that will be maximum because there's only one. Okay? So induction statement is Sn is true for n bigger or equal to 2. We'll use mathematical induction. Okay, so this time, even S1, like the first level, is hard. Because we are talking about all possible ways to pair these two. And there are more than one way to do this. So the regular pairing is this. What is the other way of pairing this? Cross pairing, right? This way. So A1, B2, A2, B1. So we're claiming that this is always bigger. Why should it be? Any idea how to verify this?
You can move several.
You can move this here, write this A1, B1 minus B2, move the other one next to it. Okay, so you can actually B2 minus B1, you can write this as a squared minus a1, because this is minus of that, right? So the question is this bigger than 0? Why is it bigger than 0? Yeah, this is positive, this is positive. Product of two positive numbers is positive. So the verifying it for p equals n equals 2 even requires some arithmetic. Okay? Let's see, not past the time. Okay, so we know it's true for n equals 2. Now we are going to assume it's true for n and prove it for a bigger n. Okay, so now I assume it's true. So this is this. Now I assume it's true for n. We will, so that we have, suppose we have n plus 1 numbers like this. See, this is a difficult question because you're doing very complicated analysis. You have now n plus 1 things here, n plus 1 things there. We need to verify that the maximum number you get is by regular pairing. Okay? All you can use is, for n, this is true. So what should I do? Any ideas?
Maybe we should exchange with n plus 1 element with something between 1 and n and see what the difference would be. For example, now the two elements anchored to our set is a plus a, n plus 1 and b n plus 1. Their multiplication will give us a times b, a n plus 1 plus b n plus 1. The summation will increase that much. We will switch elements to pairing and see how much it will decrease the total summation and how much it will.
Something along those lines, but if I start with an arbitrary pairing, then there's so many possibilities, right? So we have to organize that argument. We have to assume something happening.
I assume that the previous assumption is true.
Yeah.
So the pairing is A1 and B1, A2 and B2.
So you're pairing the first n numbers.
And I will check two situations.
Okay. But what if the best pairing here doesn't involve the first n matched to each other? Maybe the best one is A1 going somewhere else. That's from there. Let's do this. Suppose A1 goes to something. This is for sure is true, right? A1 will go to something. So let's use our idea, and this is your BI. So take out this and this, right? That way we already took an arbitrary starting point. This starting point is universal. It says nothing. It doesn't make our argument special. Because we know A1 goes to something, right? We call that something BI. That way, we just kept it arbitrary still, okay? So, so suppose A1 is paired by BI. So we have this pairing. Consider the rest. So the rest have these two groups. But this time, I have exact n things on both sides. Everyone sees that we took out one because we assume the first pairing is this way. And without loss of generality, I can do that. Now we use our argument. By Sn, right, these numbers has to be paired by a regular pairing. So the best thing you can get with these two is this regular pairing. But the regular pairing is this: A2, A1, A3, B2, and so on. And then we have this beginning thing too. So we have this. So this should be the maximum. If Sn is true, this is what you get. Now, this is under the assumption that A1 is paired Bi. And let's see what that gives us. So by adding A1 Bi, you get a maximum pairing, maximum sum. So the maximum sum looks like this. So, yani A1 burada, B1. So we go like An plus 1, Bn plus 1. So we assume that this is paired by Bi. And then the rest of the pairing has to be this way. And now we skip, and then it becomes regular after. So now we find a problem here. Unless I is equal to 1, this cannot be maximum.
Also, it is not a regular.
Can you tell me why? Just focus on these numbers. Just these four numbers. This product has this thing and this thing. These four numbers are related. A1 is less than A2. B1 is less than Bi. So just for this sum, I know a better, bigger sum. The bigger, better sum is actually A1 B1 plus A2 Bi. This is bigger. Than this first one. So if it will be bigger if we do this pairing. It's larger. So that means it couldn't be maximal, because even by switching these two, I get something bigger. Okay? Where is the problem? The problem is that A1 is not matched to B1. This is the reason that this happened. Okay? To avoid this happening, this happened when we choose I different than 1. So that means we have to actually, at the beginning, we have to choose A1. That means we must have A1 paired with B1. So that means somewhere here, I assume that I is not 1. Okay? So with not 1, we get a problem. So I should be 1. So I1, that means the beginning, that A1 had to be paired with B1. But does it finish everything? So now I know A1 is paired with B1. How can I use induction to finish the rest?
We have already known the maximum value of the.
Yeah. So if you're already pairing this with this, you can take them out and look at the rest. By Sn, the rest has to be regularly paired to get a maximum number. Okay? Then apply Sn to this the rest of the numbers you can pair using the thing. This gives pairing A2, B2, and so on. So we get a regular pairing. So we got regular pairing. For all n plus 1 numbers. So there are two steps here. The first step is trying to figure out with a maximum pairing, where can A1 go? Okay? And then we look at that, A1 couldn't go somewhere really big. Because if it did, you could have a problem. Because you could have something even bigger by just small swap. So that means A1 had to go B1. But once A1 goes to B1, the rest is already n numbers. You can use induction to pair them. So everything will be regularly paired. Okay? As I said, this is a little bit more than, I think, let's say the general level in the exam will be easier than this. But this is a very nice example to show, to prove something induction doesn't always mean writing like regular things and arithmetic. You have to use a lot of arguments and you have to come up with something nice sometimes. Okay? So that's all for today. And Thursday we meet on the usual time. Okay?